It kicked us out somehow. Yeah, but how do I reconnect? I'm not connected to Zoom on this computer. No, I am not. Wait. What? What do you mean it says live? Oh, over here. Okay. Hold on. Okay, mirror. Okay, we're still screen sharing. The other one. I'm unmuted. Let me start the video now. Hi, people on Zoom. Okay. All right, let's see if we've got it this time. Okay, so right, so I'll talk about some example use cases and methods, and then we'll have a 30-minute break, and then Catherine will talk about where we get labeled data sets for agriculture, what data sets exist, where you can go to find data sets or create data sets of your own. And then Ivan is going to end the tutorial with a hands-on demo of a library called Open Mapflow, which we can use to create our own classification maps or other machine learning output maps with remote sensing data. So getting started with the first session on remote sensing data and nuances. Firstly, I want to convince you for this tutorial that remote sensing is not just interesting from the perspective of applied machine learning. So it's not only interesting from taking models or existing methods or developing some variations of existing methods and applying that to remote sensing data sets. It's also interesting as an entire data modality on its own for machine learning. So just like we have images or text or video as different data modality subfields in machine learning, remote sensing data is also its own modality and comes with a lot of really interesting foundational research questions as well as applications within that space. So my hope is that in the future, like we have natural language processing now, in the future, maybe we'll have a whole subfield of machine learning of planetary data processing. So to make this parallel between remote sensing data and traditional data modalities more clear, I'm going to give a couple of examples here. So when we're working with image data, we typically have a very large set of independent samples. For example, ImageNet, we have a very large data set that we can use to train the model. And then we can use that model to make predictions for a much smaller data set, usually one sample at a time. And then we can use these models for real world use cases, like, for example, detecting obstacles for a self-driving vehicle, where we want to know what are the obstacles in the road given an image, for example. With language data, we have a very large data set of variable length text sequences that we use to train our model. And then again, we have, when we've trained this model, we can use it for inference to make predictions on individual samples again. And generally, these are kind of independent samples. Maybe they're coming from the same voice, but we're asking different questions, or it's really being evaluated one sample at a time. So then we might use a model like this to, for example, get a response from our Google Home about what the weather is going to be today in New Orleans. So with satellite data, we have the same parallel pipeline, but there's a really interesting inversion where we typically are training on a pretty small relative to the total available data set of label data. And these data are extremely sparse compared to all of the data that we have available from satellites orbiting the planet. So for example, even if we had, let's say, 5,000 examples of satellite images of maize fields, and we wanted to train a model to detect maize, this is still an extremely sparse sampling over the entire variability of maize fields that we'll see across the globe, both in space and in time. So we have a huge amount of data that we're never going to sample with our labeled data sets. And so with these satellite data, when we're using satellite data at inference time, generally we're not making predictions on individual samples that are treated independently from each other. We're taking a model that's been trained on these sparse labels to make very dense predictions that together make up a map. So rather than taking one image from here, one image from there, usually we're trying to make predictions over an entire contiguous area. For example, the entire country of Kenya. We want to make predictions about where maize is growing or what the expected yield will be in these maize fields. And so when we make these predictions, we stitch them all together to create a map. And that is the output information that's given to end users to answer questions like, what is the maize production going to be in Kenya this season? So the way these data sets are collected is satellites are orbiting. Actually, this is a little bit out of place. Let me jump here real quick to say what we're going to be talking about in this kind of the outline for this session is what is remote sensing? How are we using remote sensing data as inputs to machine learning models? How are we using these outputs from the models? And some important considerations for using these data. So let me just hop around here. So firstly, what is remote sensing data? It's these data sets that are collected by satellites. Also, remote sensing also includes drone or aerial images and other kinds of sensors as well. But here we're just talking about satellite data. So these satellites are orbiting the Earth and capturing images or other kinds of observations at regular intervals. So let's say every 5 days or every day, a location might be imaged by a satellite. And so these images are collected all the time, everywhere. Or they're collected on a targeted basis. So there are some satellites that are tasked, is what we would call this. So you say, I want that satellite to take a picture of this place on this date, and then you just get that one image, compared to these other satellites that really just scan the Earth constantly. And this is really different from traditional data sets that we're used to working with in computer vision, where we have these data sets that where samples are collected randomly and independently, and we don't have this global and consistent coverage. So as an example here, I'm showing the distribution of images in ImageNet and COCO, where we have images that are basically wherever they were from in the images that happen to be obtained for that data set. And this is a really big difference with remote sensing data, and actually a place where remote sensing data can be really powerful in terms of constructing data sets for foundational research, because we have the ability to create whatever data sets we want. So, these data sets are being constantly collected over the entire globe. And so if I want to collect a data set where there's some domain shift in time because I want to study distribution shift and robustness to distribution shift, I can actually go get that real data by taking all these locations and getting the satellite data at different points in time or in different years, or from different satellite data sets or at different locations. So there's this huge archive of data that's available that we can sample to construct whatever kinds of information we want to have in our data sets. That said, getting the labels for all of those data is a whole other problem, but Catherine is going to talk more about that in her slides. So to construct these data sets, we don't have to go crawling Flickr and hoping we find what we're looking for, or we don't have to go take a bunch of images in our lab or go around the world to take certain images on the ground. We have these data sets that are already being collected constantly everywhere in the world over time. So when we're looking at satellite data, there are three really important dimensions in the data sets. So we have the spatial dimension, spectral, and temporal. And so the resolution of the information in each of these dimensions is going to be driven by the instrument that is on board the satellite. So the kind of camera it has, if it has a telescope on it, what sort of lens and whatnot. The altitude that the satellite is orbiting at. So the lower the altitude or the lower the orbit of the satellite, you might have higher resolution images because you're closer to the ground. And if you have a large number of satellites, is what we would call a constellation. So if you have many satellites, you can cover more of the Earth every day and get a higher temporal cadence. And we'll talk more about each of those dimensions in a minute. So there are literally hundreds, actually thousands of satellites orbiting the Earth right now and that are continuing to be launched all the time. Not all of these are imaging satellites. There are a large number of them are communication satellites. A lot of you might have heard of Starlink, which has a lot of satellites up. And so they're all in different orbits. Most of the ones that we're using for imaging, for creating these data sets, are in a low Earth orbit. So they're kind of lower than, for example, GPS satellites. And these data sets are enormous. So you can imagine if you're constantly taking images of the Earth all the time with hundreds of satellites over many years, the volume of data is enormous and is continuing to grow all the time. So from a company called Planet Labs that images the entire planet every day, they're getting, at least this is actually an old statistic as of a few years ago, they're getting 11 terabytes of images per day. And now, this was back when they only had like 4 bands on their satellites. Now they have 8 bands and even more satellites. So you can imagine how enormous these data sets are growing. And so all of these satellites, depending on what sort of sensor they have, are able to see in different wavelengths of the electromagnetic spectrum. And which wavelengths they're seeing in tells us different information about the Earth's surface or about what is on the Earth's surface, or in some cases below. So if we look at our familiar electromagnetic spectrum here, you can see in the little visible light sliver, that's where we're used to working in computer vision. This is where ImageNet, COCO, et cetera are. But our Earth observing satellites are imaging in that space, but also way out into near infrared, mid infrared, thermal infrared, radar. We're collecting all kinds of observations in additional bands. And so typically a satellite will have like at least 4 bands, but might have up to, 30 or even more if it's hyperspectral. And just for contrast, if anybody looks at astronomy data, there are astronomy satellites that are generally pointed in the other direction away from the Earth. And often those are looking in kind of the other side of the spectrum. But again, this is all based on like, what are the physical interactions of light that's coming from either the sun in terms of passive sensors, or from an emitted radar wave in terms of active sensors. Whatever electromagnetic radiation is being emitted and interacting with what's on the surface and being reflected back to the sensor, that's going to determine what we can actually see in the image. And so we'll see things like, depending on where we're looking in the spectrum, we can measure the reflectance of the surface. This is what we're used to thinking about with normal images. We can see moisture or like water content, the elevation or slope of a surface, the roughness of a surface, temperature, all kinds of information that we can sense beyond the visible spectrum. So as a result, our data sets have these several dimensions of XY, which we also have, 2 spatial dimensions traditionally in our computer vision data sets. And we have this wavelength, which is just RGB traditionally. So for example, in this COCO test image on the right, But we have many, many more of these bands that we want to look at in these remote sensing data sets usually. And in addition, we have this time component. And depending on the temporal resolution of our satellite data set, this could be quarterly. So maybe we have 4 images per year. So that dimension is 4. It could be monthly. It could be daily. This would be 365 dimensions. All of this is configurable based on how you create your data set. So there's a lot of freedom to create new kinds of data sets and resample the data in however you want to do for your application. So spectral resolution describes the number of bands and the coverage of the spectral bands on the satellite. So this is going to vary pretty substantially between different satellites. Some of them have overlap and some of them are designed to be to have good overlap in at least some of the bands to reduce the domain shift between different sensors. But there's still a lot of variability. So each row here is showing example spectral response in the near infrared and visible wavelengths for some commonly used satellites. In particular, the bottom 3, Landsat, MODIS, and Sentinel, are really commonly used satellite data sets. And so you can see how the spectral response varies across all of those satellites. And a lot of them have pretty good coverage in the visible and near infrared. But as we get out to longer and longer wavelengths, it kind of starts to vary. So here in mid-infrared, there's a good amount of overlap still. But then in thermal infrared, for example, Sentinel does not have a thermal band, but Landsat, well, I guess Landsat has a mid-infrared band, but it should have a thermal. Anyway, maybe that's a different one. So, so some of these, like if you're trying to sense thermal infrared, for example, is really important for looking at geochemical constituents, like what is the mineral content of a surface? Maybe if you're looking at geological components in the earth versus like shortwave infrared is important for looking at water content, especially in leaves. Radar is important for looking at textures or looking, for example, for water. Radar is really good because the smooth surface of water reflects the radar waves back in another direction. And so, depending on what you want to actually observe will influence which satellite data set you'll be able to use. So this is just an example of how a certain region looks in these different satellite bands. So in grayscale, so you can see blue, green, red are what we're used to working with. And then as the wavelengths get longer into near infrared, shortwave infrared, we see that different pixels on the surface are brighter or darker in these different wavelengths. So spatial resolution is the area on the ground that is covered by each pixel. So if we say a satellite has 1 meter per pixel spatial resolution, this means that every pixel in the image corresponds to a 1 by 1 meter square on the ground. And so you can imagine that that's really going to influence what you can see and what you can make predictions about in your data set. If you're trying to look at individual houses, you're not going to be able to use a data set that has 100 meter per pixel resolution unless you have a big house. So here's just some examples of the same area in Kitale in Kenya, and how that looks in different satellite data sets with different spatial resolution. So here, for example, there's, one second, I just remembered we forgot to record, or are you recording? Okay, good. All right, so here's this area in 1 meter per pixel. If we go slightly coarser resolution to 3 meters per pixel, we can see some differences. Also, these are at different points in time, so they don't look identical, but this is 3 meter per pixel from Planet Labs satellite. Here's 10 meter per pixel from Sentinel-2. 30 meter per pixel from Landsat. So you really start to see some differences here. For example, in the Sentinel, we can kind of see these dots, and in Planet, we can see kind of where these individual buildings are, for example, up here in the top right. And then these start to get a little bit blurrier in Sentinel, but still pretty resolvable. Then in Landsat, we can't really see these individual buildings really at all. And the boundaries between these fields start to blur, and things get much coarser. And then with MODIS, this is much coarser resolution. So now we went from 30 meters per pixel to 500 meters per pixel. So obviously this data set is not great for looking at objects, individual objects on the surface. Is used much more for looking at really broad trends. For example, in like vegetation, greenness, and entire areas over the globe. That said, you can imagine as the resolution gets higher, the data size gets way, way bigger. And so, coarser, if you can use coarser resolution data, then you should, because it'll make your data much easier to work with. And so this is also now not looking at the visible, this is actually synthetic aperture radar, or SAR, image from the Sentinel-1 satellite. So SAR is emitting a radar wave and measuring the return signal at different polarizations. So that's what we're seeing here. The different colors are different polarizations. And so this false color. So you can see like radar is really good for looking at things like water. You see this little smooth spot here would be easily detectable, or I guess that's maybe not water, that's like some other object, but it's good for detecting things like smooth buildings or water, things that have very distinct textures, but with the trade-off that it's very noisy. So we see a huge amount of speckle in here, which is of course a problem that we need to deal with in our models when using that as input. So I'm just going to play this little video while I talk about the temporal resolution. So the temporal resolution is describing the frequency or the cadence of images taken over the same place. So for example, the Sentinel-2 satellite has a 5-day revisit time. So every location on the Earth is revisited by Sentinel-2 every 5 days approximately. Of course, this changes at the poles. The poles have much higher revisit since all of these orbit tracks are coalescing very densely at the top, but at the equator, it's about 5-day. Landsat has every 16-day revisit time. Planet, like I mentioned before, has daily revisit time. So, collectively, especially if there's multiple satellites. So here, this visualization is showing Landsat 8 and Sentinel-2. So you can see Sentinel-2 actually is made up of 2 satellites. So this is how it gets a 5-day revisit time. It gets a faster revisit than Landsat, which is only 1 satellite. Okay, so I'll just flip through these to show our same area in Kenya at different points in time. So here, this is a Sentinel-2 image of this area with some fields in particular on February 15th, 2022. This is on March 17th, 2022, April 6th, May 11th, June 15th, just the other day. And so if I flip through these a few times, you can see that there's really a lot of information in the temporal dimension. So there's a lot that's happening that we can see in there. And that was at a monthly cadence. Imagine that we also have daily, and from this satellite in particular, we have every 5 days. I just put monthly to have fewer images, but we'll see some GIFs of higher temporal cadence later. So if you're thinking about how should I choose which data set to use, like I mentioned, we have to think about what is it that we actually want to see on the surface. And so that influences what spectral bands the satellite needs to have, in terms of both the number of bands, but also the wavelengths that are covered by those bands. Those might be different depending on if you're looking at what's covering the ground versus if you're looking at the atmosphere or at oceans. We're mainly talking about land here, but there's a huge amount of work in atmospheric remote sensing, ocean remote sensing, et cetera. How large are the objects you want to detect? So if you want to detect small objects, you need a higher resolution sensor or higher spatial resolution data set. How useful is the temporal component? So if you're just trying to detect something that's not really changing a lot over time, like lakes, for example, maybe you don't need a high temporal dimension. But if you're trying to look at what is the yield of a maize field based on satellite data, you might want a really high temporal dimension because you want to see how that field is changing over all these critical times in the growing season. And also, what kind of money do you have to spend on this? Because most of them are publicly available. So the NASA and ESA, which is European Space Agency, data sets are typically free. So Landsat's free, Sentinel's free, MODIS is free, et cetera. But commercial sources like Planet or Maxar, which is kind of what you see in Google Maps usually, but you don't know the time of all those Google Maps images and everything. If you want to request your own images at that Google Maps resolution, that's going to cost money. So those data sources can be pretty costly, but Planet in particular does have education and research licenses. So for non-commercial use, you can get a lot of data for free. And another challenge with those paid ones is a lot of times they're contract based. So you can't just necessarily like ask how much is it going to cost me to get like one image of New Orleans. It's like a very complicated thing. You might get a different answer depending on who you are. So that can be a bit tricky. Okay, so how do we get these data into a form that we can use for our machine learning models as input? So the way this happens is in the life cycle of these inputs is first the satellite is acquiring these images. And then these images get projected onto a grid of the Earth's surface based on where that satellite knew that it collected the image. This is called orthorectification, where you're taking this image and putting it like a paper mache kind of over the Earth's surface on top of this grid. And then the image that we get from, for example, ESA or NASA is the tile, so this particular like grid tile, and whatever data for that date was actually present, or like what the coverage over that tile was. So if on June 16th, the satellite took a picture over New Orleans, but the track was like a little bit off of this tile, we're gonna have all this missing data on the side of the tile like you see here. So this is that kind of paper mache thing that's happening. So we get these images like into this gridded format that's defined by the band, the time and date that it was collected, and the location. So then from there, we have to somehow take this image and put it into, or take this stack of images over time and put them into the appropriate size and format, et cetera, that we want to go into our model. So put it in our whatever tensor dimension we want. And of course, all of those have a time band that's not even being shown here, but so these images, these grid tiles tend to be very big. So for Sentinel-2, the image that we get from those data sets directly is 10,000 by 10,000 pixels, just for one date. And so there's a lot of information in that. We're not going to put that directly into our model. We have to somehow take patches of it or do something to transform it into maybe a 1 by 1 dimension. So just each pixel individually, if we only want the time series, or 224 by 224, et cetera, et cetera. So we have to further process that into the dimension of our model input. And in addition to just getting the input in the right size, there's a lot of pre-processing that has to be done to get the data to be what we would call ML ready. So we have to do radiometric correction, which in a lot of cases is already done on the data set and provided for us. So the atmosphere is in the middle of the satellite and the ground. And so the atmosphere can add some kind of distortion or effects that we want to remove to clean up our signal. We have to mask out the clouds. So there's a lot of clouds on Earth, and even more depending on where you are. And so you see in this image on the left, this is a PlanetScope time series before any corrections have been done. So this is before radiometric calibration or atmospheric removal, before we've done any cloud masking, before we've gap filled to get rid of the gaps where clouds were or where these missing data kind of black stripes are, all these things. And often there's even some misalignment that we might have to deal with. There might be some outliers. So we have to do a lot here. But then, so this is an example where, again, on the left, this is before any pre-processing. In the middle is a data set that is available from NASA called Harmonized Landsat and Sentinel-2. So there they've harmonized the Landsat and Sentinel-2 data sets to have the same kind of grid and spatial resolution. And then on the right is the result of doing some very computationally intensive processing to get a gap-filled, cloud-free, totally clean time series, which is really like the dream for our models, but is really difficult to get to. Fortunately, we don't have to do this completely from scratch all the time. There are lots of platforms that have come up, especially over the last several years, to help with taking these source data sets and transforming them into the pre-processed ML-ready versions that we want to use as our model inputs. So, for example, Google Earth Engine hosts many satellite data sets and other geospatial data sets on Google servers. You can do your pre-processing on their servers and nicely parallelized and everything for free, and then export the data. You can export it in GeoTIFF formats, or you can even export it as TF records. There's different options there. And so you can do like images or time series. It makes it really easy to align inputs from multiple satellites in particular. So if you're like, oh, I want the data from MODIS and from Sentinel-2, you don't have to like align their grid systems on your own or all of these complicated things. You can just, it'll align it for you at whatever resolution you want in Google Earth Engine, which is super nice. There are also some other platforms that have come available recently. So Microsoft Planetary Computer is pretty powerful. They've made a lot of updates to that in the last year or so. Descartes Labs is another platform, but I think it's a paid platform, but I've heard good things about it. I don't personally use it yet. And Pangeo is a kind of an ecosystem of Python libraries that have been developed for making geospatial data easy to use. So it includes, for example, a package called Xarray, which kind of makes working with tensors like working with pandas. So it adds like named dimensions and easy interpolation over time or spatial dimensions and things like this pretty easy. And then also OpenMapFlow is a library that we've been developing that Ivan is going to talk about, which in particular is designed to make that dense inference part of the pipeline really easy. And we also have a crop harvest package that we've developed to make it easier to export time series satellite data with multiple satellite data sets anywhere in the world. So when we're using these data, or when we're taking our machine learning models and making predictions and then using the outputs of those predictions there's some important distinctions from what we traditionally think about in computer vision, machine learning. So I mentioned this before, but here, when we're working with remote sensing data, typically we're applying the model in this dense, what we call dense inference paradigm, where we're taking this entire region of data, making predictions over every location within that region and stitching it all together to get a final map. So that's what this diagram is showing here. And so these, basically, we have to do a lot of work to make our inference as well as our pre-processing scalable. So in a lot of problems, we're used to the model training being a really computationally intensive part of the pipeline, and inference is much cheaper. But here, training tends to be pretty lightweight compared to inference because of this setup. But this also presents a lot of interesting new research challenges. Like, for example, how do you evaluate a really dense map like this when you only have very sparse labeled data, and there might be a gap between that. So we'll talk more about that too. So finally, I'll end this section by talking about some things that are important to keep in mind when we're working with this exciting modality of remote sensing data in computer vision and machine learning generally. Spatial autocorrelation is a really important thing to keep in mind, where for example, two images that are within the same crop field are going to be much more similar to each other than, you know, two images from different crop fields in different countries in particular. So we have to think about what is the independence between images that might be right next to each other from the same location, same point in time, et cetera. And that's really important for how we design our training, validation, and test sets in particular. So we don't want to have this spatial autocorrelation between our training and validation sets or our training and test sets. Otherwise, we will inflate our evaluation metrics. So this is like a huge problem in the remote sensing community generally. Is you know, a lot of things have this spatial autocorrelation. So important to keep in mind. Visualization and error analysis are also really important. It's not as easy as with ImageNet or COCO, for example, to look at, oh, which are the ones that I misclassified, and I can look at them all easily at one time, see what some certain trends might be, and do some diagnosis. It can be pretty challenging to even visualize the data sometimes, especially because the data are not even like PNGs or JPEGs. It might be a TIFF. Or a GeoTIFF, which you can't open in preview. You know, you have to use specialized software or load in Python or whatever. So despite that being challenging, and again, there are a lot of libraries, for example, in Pangeo for helping with that, it's super important to do. So for example, if you have, this is an example where we had some blocky artifacts in our output, but by plotting that output map alongside the, you know, we suspected like, oh, this looks like a coarse resolution satellite bias. So there was one data set that was really coarse resolution, which was climate data. So like the precipitation and temperature, which I plot, the grid on the right is plotting. By showing those together, we can see, oh, these blocking artifacts appear to be on the same grid as the climate data set. And that's probably where these errors are coming from. I mentioned this briefly before, but there is a really often big gap between what we get from our evaluation metrics, which are based on very sparse labeled data. Even if we have a pretty large test set, again, it's very sparse compared to an entire dense area map. And so, you know, you might get 95% F1 score and you're like, yay, what a great model. And then you look at the map and it's got all of these blocking artifacts, or it's got like really blatant errors that are just not captured by that sparse labeled set. We have distribution shift or domain shift between sensors, particularly, I mean, sensors, you're like completely different domains often. So you might have a visible satellite or a visible data set versus a radar data set, which will be very different. We have these distribution shifts, especially in space and in time. So, you know, if the climate is changing and there's over time in the long term, but there's also pretty significant shifts between different seasons or individual consecutive years. And so being able to be robust to these distribution shifts as time goes on and we use our models in future years or we use them in different locations is really important. This is just an example of time as well. So here I'm showing like the same date of some fields in Illinois, in the US on June 13th, 2018, where we see a lot of these fields have been growing quite a bit already. And June 13th, 2019, so the same day, but in the next year, things have barely been planted. And so you can imagine if you're using something that's looking at the time dimension in particular, this would be a pretty substantial shift for your model. Another important distinction is that often the labels that we're using, Catherine will talk more about this in a later session, are georeferenced shapes. So we might be going to a location and recording, you know, at this latitude and longitude, maize is growing in this field. But depending on the satellite data set that gets paired with, you know, those might not be all perfectly aligned. So there might be some misalignment between the data sets and our labels. And especially for things like, here's some examples of field boundaries, which are polygons that are georeferenced. Those might be, you know, not exactly aligned on different data sources, which can be a problem. And you also have to think about using the right date for those. So even if I recorded that, you know, there's a building here in 2022, in 2025, the building might be gone, or a forest might be gone, or a crop field might be gone, might be something else. So our labels are not always valid through time. This is actually an important thing with using the Google Maps API for getting images is you don't know the date that those images were collected. So they could have been 2000, could have been 2020. So you have to be careful when you don't know the date and if it corresponds to the date of your label. And finally, existing architectures in computer vision are not typically designed for remote sensing images. So there are important distinctions in these data sets that we're sort of missing out on in a lot of existing architectures. I think there's a lot of space for doing novel research in. For example, the objects tend to be very small that we're trying to detect with respect to the full image. And so this has important implications like how deep your convolutions should be. You know, the visible field or the receptive field for your model should actually be much smaller with a remote sensing image. You don't want super deep convolutions a lot of times because, you know, what's on one side of the image is not necessarily useful for what's on the other side of the image in terms of predicting whatever the class is, which is very different from, for example, in this Coco image, you know, knowing that there's a wheel here in the bottom left and a handlebar here in the middle, you know, getting that context in our deep models is useful, but we tend to see shallower models performing better with remote sensing. There's also lots of textures, not so much like very distinct visual shapes in our data. We have these multiple scales, et cetera, et cetera. And interestingly, for a lot of tasks, a random forest is still a very competitive baseline, which I think shows that there is a huge amount of opportunity to innovate beyond what we have from, or what we've developed in terms of architectures for existing vision data sets for remote sensing. So there's a list of resources. This is also on the tutorial page that you can look into if you're interested in learning more about these data. And with that, I will end this session, and maybe while we transition, feel free to come up and ask any questions. But next, Catherine will be talking about Earth observations for agriculture. I'm very over time.
All right, so I'm Catherine Nakalembe. I'm an associate research professor at the University of Maryland with Hannah and Ivan. And I will just generally talk about, give an overview of how Earth observations are used in agriculture. And I'd like to start off with some big question, I guess, to kind of form the basis for where all of this started. And I wonder how many people in the room can, just a quick answer, what is food security? So we're just going back to kind of like the meaning of all of this. A quick response. Food security? Nod if you don't know. No, I saw a nod. So food security really just means that people have food at all times and are not worried about food, so they don't have to think about it. And it has many components, and these include availability, access, utilization, stability. So it's not about, I don't know, having a bunch of bad wheat and you eat that, that doesn't equal food security. And so agriculture monitoring is sort of the basis is basically that we want to know how much food is available where. We want to know the quality of it. You want to know if people have access to it. And it's very complex. And in terms of where we stand today regarding food security is that we're doing pretty badly. It's sort of something that is more common than you think. For example, in the US, there's food insecurity. I think approximately 2 million people in the US were food insecure in 2020. That means they're worried about, where they'll get their food tomorrow, or they can't afford what they'd like to eat. And a lot of it is sort of ingrained in people not being able to afford food, rather than that there's enough food available for people to buy. And it's sometimes related to access. So there might not be markets where people are located for them to access food. And of course, this has gotten more complicated with COVID, with conflict, with more people who are being displaced. We have more climatic challenges that are making more and more people food insecure. And there are several ways that we can try and address these complexities. So food security is a global problem. It's everywhere. And so the rest of my talk will basically focus on how we're using Earth observations to address some of those things related to accessibility, availability, for example. And so to know where food is or how much food is available, we have to start with a farmer. So a farmer might want to know when to plant, what might happen to their field if they plant. Will there be a disaster? Is my wheat the appropriate type of wheat for the region where I am? There are things like rainfall and temperature that in certain places are the defining factor for whether there will be food available at the end of the season or not, because farmers don't have access to irrigation. And some of the other things that you might want to look into if you're a policymaker is the potential for now, potential for the future. You might want to look into whether crops is suitable or if they will be suitable given changes that might unfold in the region. And this is where satellite data becomes really interesting. As Hannah showed, we have these satellites orbiting the Earth. Since the 70s, we've had land monitoring satellites, Landsat. What these make possible is that not only can we look back in time, but we can understand what's happening currently. And so there's some really interesting data sets that we can extract from these satellites, and Hannah will cover that in the next session. So this is sort of like a general overview of sort of how everything fits together. It's simplistic, but basically we have satellites collecting data. We use images coming from these satellites. We use machine learning to extract, information like what crop is where. So cropland, crop type. We have crop conditions. We can model yield. when you combine that with other information like rainfall, temperature, their forecasts, and whatever is going on with the soils, soil moisture, soil quality, soil, the microbiome, then you can get into more detailed things. For example, when should I fertilize? If things are really bad in terms of temperature, if it's too high, there's no rainfall, then you can talk about, well, everything's going to fail, so we need to give, a signal that things are going to be bad. And this can, help a farmer, it can help a policymaker. And since we have this broad overview of really large areas, it's really useful for policymaking. And so why are observations for agriculture? Pretty straightforward in a sense. We have very large areas that we have to monitor. We can't be there all the time. We have to analyze a lot of data, and in the recent years, we've had huge advances in terms of capabilities. So you have not only, cloud computing capabilities becoming more and more available to other people, in addition to having more and more satellite data. So being able to combine that and use it at the same time has made it possible to be able to do larger scale analyses. You can do a whole bunch of experimentation you were not able to do like 5 years ago. It can inform policies. I already talked about this. But what is really cool, I think, from my perspective, is data and methods for everywhere. So we have the same satellites, but once you start digging in, you realize you need to do a little bit more in some places than others. You may need to deal with more complex data sets, messy data, missing data. So some of the, if you start going back in time, you might find that there's very poor coverage of certain satellites because maybe the satellite downlink for that area didn't work. So you can't go back in time. And so just some cool pictures of how farms look like from space. An example from Kazakhstan, this is in a sort of like an alluvial fan. This is what crop fields look like there. We have an example from Saudi Arabia. This is irrigated agriculture. It's really cool because I didn't have to go there, and I can understand how fields are performing in that area. An example from the US, you can see different fields in different stages. You can see the circular ones, which are irrigated, and others that are not. And here's an example of rice in the Mekong Delta. So you can extract information about the sort of the status of rice in Vietnam without sort of physically being there, but it's a lot more complex than that. And when you put all of this together from a global perspective, you can understand, for example, where maize is growing, where wheat is growing in the summer, where wheat grows in the winter, where rice is growing, for example. And why would you want to know, the differences? Why would you want to know all of this? If there is a drought in India, let's say, for example, this year, where a majority of our rice comes from, we might have a rice crisis on us. If there is a drought in the winter for where winter wheat comes from, that has a significant impact on wheat availability. And we all eat bread in some form, so that can have huge consequences. And so you need that kind of information and that level of detail. And so combining satellite data, cropland, crop type, vegetation conditions with things like temperature that we have access to from all over, data sets like rainfall, so precipitation, runoff, soil moisture, can help us understand how much water is available for crops, how hot it is. So certain crops have a sweet spot in terms of temperature, where you can't grow maize, for example, in Canada, or you can't grow grapes, for example, in South Sudan. And so this is really important for if you want to improve policies that might make available maybe drought resistant wheat, or if you want to address those types of things. And combining with the fact that climate is changing, when you put all of that information together, you can better kind of assess where you might want to get food in the future. And so we can look at vegetation conditions. I don't think that's going to work, so I'm just going to skip over it. And why might this be important? So I apologize for the quality of these maps. It's not my fault. But what it's just trying to show is that the top left is where maize is grown. I believe the green one right here, if you can see my cursor. And then this is showing maize yield. And so even though there might be a lot of maize in a lot of places, maize yield is highest, for example, in the US and Europe. And if there's a drought in the US, there might be huge consequences for maize prices, for example, around the world. And we're only able to have this kind of view of this because we have satellite remote sensing. There's no other way that you'd be able to have this type of information, I believe. And so, and what would we do with it? There's quite a lot of things that we can do with having, it's, you know, a lot of power, having this type of information. I think the beginning of spying started with spying on the food availability. So if you know that there is no food, for example, in a certain region, you can hike your prices so they can buy it from you, or you can just, you know, close the stores and cause a whole bunch of problems in other places. And so moving on, just to give some examples of what else we can learn, what we can do. So we can predict or understand where and when droughts are likely to happen, how severe those droughts will be, and droughts have impact not only on crops, but livestock. And one way we do that is you can combine rainfall derived from satellite data. If you combine it, well, high temperatures, that would equal very dry soils, which means no water is available for vegetation. Then you have poor conditions, which could be equivalent to drought conditions. Then you have failed crops. There's reduced food available when crops fail. And then we have food insecurity. So like you can kind of look at all of these things in sequence, but it's because you have access to all these data sets that are being collected sometimes at the same time, but in a very timely way. And then this is an example of current conditions. Generally, this is from a GLAM system. It's developed by the NASA Harvest team. And it's just showing like crop conditions globally, basically. You can see the red spots. It's really tiny, but you can see the red spots are where there might be below average conditions. And you can see that, for example, down here in Mexico and in the Midwest, everywhere that's brown is slightly below average. And so we already have too many problems so going on in the world, but then having this broader view also makes you think that, oh, it could get worse, but we need to do something about it. An example from Kenya, right now in East Africa, I think this is the 4th consecutive drought affecting all of Eastern Africa. And we can look at it not only visually, looking at where the anomalies are, but we can look at it looking at time series plots where we can see where now fits within the history. So if there was a point in time, so the blue right here indicates where before the beginning of June, where crop conditions were, in some instances, it can be way worse than that. And so this is really helpful because I don't need a very fancy computer to access this information, and anybody in the world can go in and kind of look at what's going on. So my last example about the utility and the usefulness of this information is that just those simple anomalies. So this is useful because you're combining cropland. In this case, there was no crop type, actually. So we have cropland, we have vegetation conditions from the normalized difference vegetation index from the MODIS satellite, combined with rainfall, combined with temperature. There's a design, this program, the example that I'm showing was designed purely using those data sets. And with it, they were able to predict when there would be a drought. And 3 months before there would be sort of a big problem, they would make this money available, and the community would do something else rather than continue to work in their fields. And this is one example where they sort of quantify the impact of having that early warning coming from using these data sets. And over the 5 years of the program, they saved $11 million. And how they saved them is this. So they still spent money on early response, But instead of reacting at the end of the season or the months when everything's going really bad, they would have a little bit of time to plan, which means they're not rushing to buy highly priced, very expensive food in emergency situations. And things move a little bit slower and there's better planning. And in a process supported over 90,000 households. I think it's approximately about 300,000 people. And so just very simple things, but simple things that I sort of founded in very good, well, one, available data available everywhere. Second, very good methods that have gotten way better than where they were at that time. We can do much more complex analyses now. In addition to working towards sort of transitioning these very sort of complex, far removed things and putting them in the hands of the people that make decisions. And so those are some of the things that are generally important in terms of transitioning from research, applied research into decision. And so we've saved some time. And so we've finished the overview, and I believe Hannah is going to give us some examples of use cases and kind of go back into machine learning.
Yeah, so hopefully everybody's super inspired to work on methods in this space now, if you're not working on them already, and thinking, what kinds of tasks can I work on towards addressing these? So that's what we're going to talk about next. If I'm able to find it. Okay. All right, so we'll talk about some use cases and example methods. And by the way, I'll keep us at the 3 p.m. break. So we'll still have time for our 30-minute break. So when we're thinking about, okay, within all of the things that are important to work towards with what Catherine presented in terms of what we can monitor in the world of agriculture and food security using Earth observations data, what's interesting in terms of remote sensing data, and what's interesting in terms of AI, including many topics in machine learning generally and computer vision. Kind of the core topics at the intersection of those are what I'm going to talk about here. So this is not an exhaustive list by any means, but these are really like the main tasks that people are working on at the intersection of these 3 fields right now. So these include crop mapping, crop type mapping, field boundary delineation, yield estimation, and pest and disease detection. So there are other kinds of things that people are doing. For example, detecting farming practices. Maybe you want to detect if there's irrigation happening, or you want to prescribe irrigation at the field scale, or you want to map soil types, et cetera. But those are still like fairly small research areas. So these are kind of the core ones that we've listed that we feel have kind of the broadest impact across this space. And a lot of these other types of methods, like those I mentioned, also map to similar kinds of problems that we would use to solve these. So for example, crop mapping and detecting whether something is irrigated or not is just binary classification. Crop type mapping is multi-class classification. Field boundary delineation, we're doing segmentation. Yield estimation, we're doing regression. Pest and disease detection, we often treat as an anomaly detection or out of distribution detection problem. And so within all of this, using the fact that we're using remote sensing data with all of these nuances that I described before means that we have a lot of interesting other research problems within domain adaptation, distribution shifts, multi-fidelity data fusion, how do we learn from limited labeled data, all of these different topics that we can study in the context of remote sensing data and agricultural applications. So I'm just going to go through each of these topics here and describe what it is, and also one or two example methods that are being used to address that task. So crop mapping, again, is just mainly binary classification of pixels, either as crop or non-crop. Sometimes you might also see this as what's called land cover classification, which would be classifying multiple classes like water, buildings, agricultural fields, forests, etc. But usually when we're talking about crop mapping, we're talking about this binary setting. So we input some satellite data and out we get a classified map of that data where we're distinguishing between pixels that contain cropland or do not. This is an example from China. And so one example that we've worked on in our group is shown here. So we had a project where we wanted to classify cropland in Togo, and more generally, we use this approach for classifying cropland everywhere in the world, in particular where we have limited labeled data in a given region. So the way we do this is we have a very large data set, which contains global samples. So we have in our crop harvest data set that I mentioned before, we have over 90,000 labeled examples globally distributed of crops and crop types. But within a particular region, such as Togo, a country in West Africa, we might only have 40 or a couple of hundred labels, very much smaller data set. And so how do we use these data sets together in an efficient way? So the way we do that is we have a multi-headed model, which in this case was an LSTM, but it doesn't have to be an LSTM. You could use different types of architectures here. So it's basically a multitask learning setup where we have two outputs, one path that's taken for the global distributed data and one path that's taken for the local data. And so the model takes in a 12-month time series of Sentinel-2 satellite observations at all of those label locations in all of these spectral bands that Sentinel-2 provides, and outputs whether there's a crop in that location or not. And we encourage the model to learn from the global data set, but specialize its features that it's learning more towards the local data set by using a loss function that penalizes the model more for getting local samples wrong. So if the model gets one of the Togo samples wrong, it's penalized more than if it's an example in China. And using that model, once trained, we applied it over the entirety of the country of Togo to create a map like this one shown on the right of cropland in Togo. So crop type mapping is similar, but here we're classifying every image or pixel location, generally a pixel location, into one of N crop type classes. So maybe in this example, this is the USDA cropland data layer, which is a random forest result. There's classes of corn, soybean, sweet corn, alfalfa, wheat, water, all kinds of things that it's like, I don't know, over 100 crop types that are growing in the US that are available every year in that map. So that's the kind of result that we're trying to get. We input the satellite data and now we get a prediction of one of N crop type classes. So one example of this is this paper, multi-crop classification in Ghana and South Sudan by Rose Rustowitz when she was at Stanford, where they, this is super small, sorry about that, on the right side. But what this is showing is basically three kind of units with convolutional LSTM units in taking in 3 different satellite data sets. So it's taking in planet data, which was that high resolution, high spatial resolution, daily cadence data set, plus Sentinel-1 data, which was the synthetic aperture radar one, and Sentinel-2 data, which is the optical 5-day revisit one, and processing all of those through individual units, and then joining the features extracted by each of those at the end of the network to make a final prediction based on all of those satellite data sources of what the crop type was in each of those pixels. So here we actually have a segmentation output, but in a lot of cases, this is done on a per pixel basis too. And I'll show an example of that as well. So you can see here are some input examples. So they've taken these little patches of much larger satellite images, and they obtained these target labels, which are where these different crops are in the fields, and then compared several models, including their own and a random forest, always a surprisingly competitive baseline for classifying those multiple crops. Another example, crop type classification can sometimes also be posed as a one versus rest binary classification problem. So this is especially useful when you're trying to build a model that you can use for classifying crops that you might not have planned to classify. So maybe in this year we have banana, maize, and soybeans in our data set. But then next year we get some data for wheat. Well, we don't want to have to completely retrain our model to have all of the output classes, really like open set classes here. We want to, an easier way to do this would just be to do one versus all. So we have a separate model for each of the crops. This is what a lot of people do operationally. So one approach that we've done for this is called task-informed meta-learning, or TIML. So the idea here is that this is a variation on model-agnostic meta-learning that enables context between tasks to be learned by the model, which is especially important for our geographically defined tasks. So our tasks in this data set are classifying different crops in each country. So one task might be maize versus rest in Kenya, another might be wheat versus rest in Ukraine. And so here we're able to learn, using this approach, we can learn, for example, that classifying crops in Kenya is more similar to classifying crops in Tanzania than it is to classifying crops in Ukraine. So this provides a way for learning context between tasks when we have this metadata, any metadata available at the task level. So in this setup, we have a task encoder that takes some task specific data, which in this case is the location of the points, so the latitude, longitude, as well as the category that we're learning. So whether if it's a cereal type of crop, a tree type of crop, some metadata that we have at this task level. And then we encode that task vector using a separate network. And then that is used to modulate the hidden vectors of our model, which in this case, we use the same model that I showed in that Togo example, that LSTM, but could be used for any model where you have gradient-based training. So, or where you would use meta learning and where you have task level information. So kind of the intuition for this is that TIML enables us to push the weights of the initial weights learned by mammal in a direction that's closer to the optimum for each task. So this modulation is applied before the task fine tuning even begins. So it's kind of nudging the weights closer before it starts to fine tune, and hopefully learns more efficiently, gets closer to the optimum weights for that task by having this prior from the task level information. And so using this, we've shown pretty substantial improvements to other baselines for crop type classification, as well as compared to just using vanilla mammal. So the next one I'm going to talk about is field boundary delineation. So this is segmenting the individual boundaries of crop fields, or you might also call them parcel boundaries. So that looks like this example here, where we have a satellite image and we want to identify a polygon really for each of those individual fields. So this looks a lot like an instance segmentation problem. One example of this is from a paper by Sherry Wang and co-authors published this year, where they built a model for field boundary delineation using transfer learning and weak supervision. So the idea here was that because you don't have a lot of labels in some places, but you have a lot of labels in other places, similar to the Togo example I showed, you want a way to make as much use as possible of those large available data sets to help you learn more efficiently from your small labeled data set in your region of interest, which in this case was India. So in this use case, they had a very large data set of field boundaries in France that's published every year by the French government. It's like the boundaries of every single field in the country, a huge data set, really high quality, really densely labeled. In contrast, they had some pretty sparse and sort of randomly distributed, not completely labeled regions of field boundaries in India. And so they basically pre-trained a model on the labels from France and then fine-tune that on the labels from India, but also do some other fun transformations to make the images from France look a bit more like the images from India by using different data sets with different resolutions, since the fields in India tend to be much smaller than those in France. And so another component of this, and this is actually pretty common with remote sensing data sets, is we need to use weak supervision. So if you have an image where for your training data set and you only have one of 30 fields in the image labeled, well, we don't want to label all of the unlabeled ones as not fields, or have the model learn that those are negative example. So we use weak supervision to basically mask out the pixels in the loss that are not labeled. And they use a model called Fractal ResUnet, which includes a self-attention layer, skip connections, and an encoder-decoder architecture. So another common task is yield estimation. Probably something you saw a lot of in Catherine's talk is people want to know how much food or how much crop volume is, or crop weight is this field going to produce at the end of the year? And what is that aggregated estimate going to be over an entire county or country? So yield estimation is just estimating what that harvested amount is going to be per unit area. So this would be expressed in units of, for example, kilograms per hectare or bushels per acre in the US. Or in this case, tons per hectare. So this is showing an example yield map of taking all the satellite data over the entire US and producing a map of the yield in multiple years for maize fields in the US in this particular paper. So one method that I'll give as an example that has been designed to solve this problem is from Yu et al. In 2017, it's presented at AAAI, called Deep Gaussian Process for Crop Yield Prediction based on remote sensing data. So their goal here was to predict the county scale yield. So they weren't trying to predict in every single field what the yield was going to be. They wanted to predict in every county in the United States what the yield would be based on the remote sensing observations. One challenge with that is that if you were to take all of the pixels in an image of an entire county, this would be an enormous image, right? So this is way too high dimensionality to use as an input to the model. So we have to reduce that in some smart way. So the way they did this was by creating 3D histograms that they used as input, where these histograms, or the 3 dimensions of these inputs were the spectral band. So they here in the top left is showing, it's really hard to see for you guys, sorry, but each row is the histograms for a particular band. And then they have those over time and also binned into spectral reflectance bins. So we have histogram for every point in time and for every band. So that gives us this 3D input. And then they use that with 2 different architectures. So they evaluated using an LSTM and a convolutional neural network architecture implemented with a Gaussian process component to try to explicitly model these spatiotemporal relationships, and did a pretty good job with estimating yield. Recently, we also took this same data set that they use and we evaluated this task using the TIML approach, task-informed meta-learning, that I showed a minute ago for crop type classification, just to show an example of using that approach with a different architecture and kind of entirely different setup, different task, a regression task rather than classification. We showed that using TIML, we could get better performance than the prior methods using the deep Gaussian process with both the LSTM and CNN architectures. So here, this is showing their LSTM with the Gaussian process, with MAML and with TIML, and then the CNN with the same. And so again, adding this context information that we have available about remote sensing data and how they relate to each other, how these examples relate to each other can help us learn more efficiently from those data, which is not something that we often have with this metadata for computer vision data sets typically. So that's another, I think, exciting aspect of remote sensing data. So finally, looking at pest disease and generally what we would call hotspot detection, meaning things that like we don't want to be there. I think Lorenzo had a presentation yesterday talking about weeds are just things that humans don't want to be there. So this is the kind of thing that I'm talking about detecting here. So detecting in-field anomalies generally that represent some unfavorable condition as defined by humans. And so an example of that here is, this is a high resolution image from a satellite called SkySat from Planet Labs, which used to be owned by Google. SkySat used to be owned by Google. And you can see there are these kind of bare spots within the field that are actually where downy mildew disease is growing on these Chardonnay plants. And so on the right, this is showing the anomaly score from one of our models that is detecting where in-field anomalies might be. So the bright yellow pink pixels are showing higher anomaly scores and the darker ones are lower anomaly scores. And the way we did that is using a method or really a toolbox that we've developed called DORA, Domain Agnostic Outlier Ranking Algorithms, which is a package that combines several different outlier detection algorithms and makes it really easy to apply them and compare them to different types of data. So in that we have some kind of traditional distance-based methods like the Reed-Shawley method, PCA, isolation forest, negative sampling, which is a method proposed a couple of years ago, probabilistic autoencoders proposed like just last year. and some different baselines, and also includes some tools for visualizing and evaluating and organizing the outputs of those. So this particular output on the left is actually from local RX, which is just scoring each pixel based on the Mahalanobis distance between the pixel and its local surroundings. So there's not even any deep learning within that one, but within Dora, we have, for example, probabilistic autoencoder, which involves neural networks. So this is one example of solving this task or of addressing this task. But even though this is like widely understood to be an important problem and a lot of people want this, there's still very few studies that are using modern vision or machine learning methods for detecting these anomalies within remote sensing images and fields. For the most part, what we see are studies that are using these techniques for ground-based imaging. So you might have even seen a lot of examples where it's like a farmer has a phone and they take a picture and they're like, oh, what's this disease? And somebody messages back saying what kind of disease it is, how you might treat it, or detects it, something like that. And this is great, these are really powerful, but the reason I share this example is because, this is so fine scale. Like this involves like somebody being in the field, going out every day, checking what's in the fields, which can be really large areas and difficult to get to. Whereas there's a huge amount of promise with remote sensing data to be able to just immediately see these entire areas where there might be anomalies without ever having to go into the field. So using those kinds of data, we can alert farmers, for example, hey, you might want to go drive over to that area and take a look at your field, rather than them having to survey all of their fields all the time, which is extremely time consuming. So there's a lot of space for research in that task. Okay, and then I just want to make this distinction. I know I said we'd end at 3, we're a few minutes late, but I'm almost done. So a key difference here is when I'm saying mapping versus classification. Again, with classification, we're generally looking at individual samples that are treated independently, whereas when we're talking about mapping, we're talking about stitching these outputs together to make the map, which is what people want to use in the end. Okay, and then I've just listed here, I'll briefly go through some open challenges across all of these problems. And again, we're looking at this niche of the intersection of agriculture, remote sensing, and machine learning, but these are really broadly applicable to not just agriculture. So again, I mentioned before that the algorithms and architectures that exist today are not usually designed for remote sensing data and real world challenges. So there's a lot of opportunity for designing new algorithms and architectures that work really well for the nuances of these data sets. For example, the temporal domain is often much more important than the spatial dimension here. If you look at this GIF on the right, a single input, once you put it in the size that we want for a CNN, for example, might be entirely within one of those crop fields. So, it's not going to tell you a lot about, spatially, it's not going to tell you a lot about whether that field is maize or soybean or wheat, but the temporal dimension is extremely rich in that information. I mentioned also several times, there's a lot of opportunity for improving robustness to distribution shifts, both in time and space, mitigating this training data bottleneck. So a lot of challenges in this space are stemming from not having enough labeled data. There's a lot more room for people to make their data and methods openly available. This community is great about doing that. The remote sensing community is a little bit behind in terms of openness, but that's certainly changing. We need a lot more flexible tools and processing chains for scaling these methods to be able to use them in practical applications, which I think is probably clear once you've seen these data volumes and the kind of processing we need to do. There's a lot of room for more interdisciplinary teams of machine learning researchers and domain scientists. So, looking at our team, for example, Catherine's background is in agriculture and remote sensing. My background is in machine learning, and Ivan as well. And so we can only do this kind of work when we're working closely together as a team, because we can't know all of these different aspects deeply on our own. And also, related to that, I think is capacity building and end user engagement. So there's a lot of room for, use inspired research, talking to people about what they actually want us to be doing and solving challenges to help them do that, not just working on what we think might be interesting, but might not be usable in the real world. And then finally, making models and data sets that are usable by everybody in the world. So, we can't always assume that people have many GPUs to use or any GPUs to use. And so that's really important, not just thinking about globally, but even working with rural communities in the United States. So with that, I will leave everybody to the break, and we'll be back here at around 3:30. There's a question in chat.
What are your thoughts on the use of self-supervised, i.e. not
Mhm.
the data sets, even
Yeah, that's a great question. I'll repeat the question. So the question in the chat was, what are your thoughts on using self-supervised methods? A lot of them. So there's a huge opportunity for this. Actually, there's a paper that we recently published on a need for developing foundation models for remote sensing that can be used as a starting point for working on a large number of these tasks, which again, thinking about access to compute and the ability to train on these really, really huge data sets especially unlabeled data sets that we have available with remote sensing. We have the entire planet every day for years. This is so much data that we could train in a self-supervised manner. I think it's yet to be done effectively. So that is a big opportunity. And we're working on putting out a data set now of benchmark tasks that can be used to evaluate these self-supervised models. So fine-tuning tasks basically across a range of problems like involving crops, livestock, atmospheric things, all kinds of wide range of Earth observation and climate related benchmarks. All right. We'll see you at 3:30.